In probability and statistics, real-world data collection is essential for understanding how variation occurs naturally and how statistical tools are used to describe and interpret this variation. The pulse interbeat interval IBI, the time between two successive heartbeats, provide a suitable biological measurement for this purpose because it is fluctuate due to psychological factors such as breathing, posture, and activity level. By measuring and analyzing the IBI, students can observe how randomness appears in every biological processes and how probability concepts apply to the continuous data. The purpose of this experiment is to collect 30 IBI values under controlled conditions and use them to explore the key of statistical ideas, including probability estimation, empirical frequency, sample mean, sample variance, and conditional probability. Through this experiment, students can learn how to compute probabilities from the real data, determine how closely observations cluster around the mean, and interpret relationships between events using conditional probabilities. And overall, this activity strengthens students' practical understanding of statistical analysis by connecting theoretical concepts to measurable and meaningful biological data. Tools and setup. First, smartphone with pulse tracking mobile and smartwatch application. Second is stable chair to minimize movement and keep posture constant during data collection. Third is pen to record each IBI measurement accurately. And fourth, camera to record the document experiment setup. Number of trials 30 and the environment is indoor classroom. First, sit quietly for 2 minutes. Second, measure the time in seconds between two successive heartbeats. Third, collect a total of IBI readings. And fourth, avoid talking or moving during the entire measurement process.
Today, I will explain the calculation for the sample mean and sample variance of the interbeat interval readings. First, for the sample mean, we use the formula EX equals the sum of X times the probability of X. This means we multiply each interbeat interval value by its probability and then add all of them together. After calculating the sample mean is 0.8207 seconds, this tells us that on average, the participant's heart took around 0.82 seconds between beats, which is considered normal for a resting heart rate. Next, we calculated the sample variance to see how spread out the readings are. We first found EX squared and then used the formula variance equals EX squared minus the mean squared. And then after substituting the values, the variance is 0.00200062, which is very small. A small variance means the readings are tightly clustered around the mean. In other words, the participant's heart reading was very stable and consistent with very little fluctuation during the measurement period. In conclusion, the mean shows a normal resting heartbeat and the small variance shows that the heartbeat was steady throughout the recording. Today, I will explain the calculation for the sample mean and sample variance of the interbeat interval readings. First, for the sample mean, we use the formula EX equals the sum of X times the probability of X. This means we multiply each interbeat interval value by its probability and then add all of them together. After calculating the sample mean is 0.8207 seconds, this tells us that on average, the participant's heart took around 0.82 seconds between beats, which is considered normal for a resting heart rate. Next, we calculated the sample variance to see how spread out the readings are. We first found EX squared and then used the formula variance equals EX squared minus the mean squared. And then after substituting the values, the variance is 0.00200062, which is very small. A small variance means the readings are tightly clustered around the mean. In other words, the participant's heart reading was very stable and consistent with very little fluctuation during the measurement period. In conclusion, the mean shows a normal resting heartbeat and the small variance shows that the heartbeat was steady throughout the recording. For question 3, we were asked to find the sample mean of the interbeat interval readings. Using the probability distribution and multiplying each value by its probability, we obtained that bar x equal to 0.8207. This means that on average, the participant's heartbeat interval is 0.8207 seconds, which reflects a normal resting heart reading. Next, we calculated the sample variance using this formula, and then by substituting the values, we got 0.00200062. Because the variance is very small, this indicates that the heartbeat readings are very consistent and do not vary much from the mean. For question 4, we were asked to calculate the probability that an IBI readings fall within. Alright, for question 4, we want to find the probability that the value of x lies within 0.03 units of the mean. We start with the expression. This means the distance between x and the mean is no more than 0.03. We can rewrite this absolute value into an inequality, and then we add x bar to all parts of the inequality, and the value of the sample mean is x bar equal to 1231 over 1500. And then we substitute it into the inequality and we calculate this value. The interval becomes like this. And then now we look at all the probabilities for x within this range based on the given distribution. We add the probabilities of all values of x that fall between 0.7907 and 0.85. After adding all these fractions, we get 7 over 15, which is equal to approximately 0.4667. So the probability that x lies within 0.03 of the mean is 0.4667 or 46.67%.
For discussion, most IBI values occur between 0.8 seconds and 0.9 seconds. The sample mean is 0.8206 seconds, which lies inside the range, showing that the reading cluster tightly around the average. Next, we move to question 5, the probability for x between 0.89 and 0.9 and x more than equal to 0.8. So let A equal to x between 0.89 and 0.9. So we decide B equal to x more than equal to 0.8. Then PA equal to probability for 0.89 less than equal for x, and x is less than 0.9. So we put the number for the calculation here. So 1 over 19 plus 2 over 19 and plus 1 over 19. So we will get the 4 over 19 equal to 0.2667. And then we move to the PB, that is equal to probability for x more than 0.8. We put all the value for it. 2 over 15 plus 1 over 10 plus 1 over 15 and so on. We will get 7 over 10, that is equal to 0.7. So the probability for AB is we will get the 0.381. For question 6, which class has the largest empirical probability? So the interval is between 0.8 seconds to 0.89 seconds. So probability equal to 11/30, so we will get 0.3667.
For this part, which is calculation of theoretical probability uniform model, so because the IBI readings appear evenly spread from 0.75 second to 0.92 second, we assume a uniform distribution, which is fx equals to 1 over 0.92 minus 0.75 equals to 1 over 0.17 equals to 5.8824. After that, we use probability that IBI is between 0.80 second and 0.88 second, and the fx is 5.8824 equals to 5.8824 multiplied with 0.88 minus 0.80 equals to 5.8824 multiplied with 0.08 equals to 0.4706. After that, we use probability that IBI is less than 0.82 second. So the range is 0.82 second and 0.75 second. The fx is still 5.8824, so it is equals to 5.8824 multiplied with 0.82 minus 0.75 equals to 5.8824 multiplied with 0.07 equals to 0.4118. So the comparison, the theoretical probability 0.47 is higher than the experimental, which is 0.63. So the difference may be due to small sample size or measurement rounding, or slight systematic bias in measurement posture or apps. If more trails were collected, the results would likely move closer together. That's all. Question for chapter 3. A. Find K and Fx. So the Fx that has been given from the question is K implies with X minus 0.75, and the range value is between 0.95 and 0.75. First of all, we need to do Fx equals to 1. After that, we put in the Fx, which is K implies with X minus 0.75 equals to 1, and the range value is 0.95 and 0.75. After that, we need to put K in front, and we will need to integrate the Fx. After we integrate the Fx, we will get K implies with 1 over 50 equals to 1. So K equals to 50. After that, to answer the next question, which is find Fx, because we only have one equation, so we will need to find only one value of Fx. So we will need to use the range between X and 0.75. So first of all, we use Fx equals to Ft, because we don't want to confuse between X and T. After that, we integrate the Ft, and we will get 50 equals to 25 x squared minus 37.5x plus 14.0625, and this is a declaration form of the question. That's all. For question B, compute Ex and variant X. So for the EX, we will use the range between 0.95 and 0.75. And then X will implies with Fx. And it will become X implies with X minus 0.75. And we will put the 50 in front. After that, it will become X squared minus 0.75x. And we can integrate it and put the range value into the X. And it will become 50 implies with 53 over 3000. And the final answer is 53 over 16, 53 over 60, or 0.8833. After that, we will need to find EX squared, which is we will use the same method, but we will just change the X to X squared. So X squared will implies with Fx, and we will put 50 in front again, and X squared will implies with X minus 0.75, and it will become X power of 3 minus 0.75 X squared. After that, we can integrate it and put the range value inside X, which is 0.95 and 0.75, and it will become 50 implies with 313 over 20,000, and the final answer is 313 over 400, or 0.7825. So for the formula of variant, it is EX squared minus EX squared. So it will become 0.7825 minus 0.8833 squared equals to 0.0023. That's all.
So for question C, to get the mu1, we will equal it with the EX. And for the mu2, we will equal it for the EX square. Mx in bracket T equal to E in bracket exponent Tx. So at here, we need to do the integration by part, the easiest way to get the value here. And we do all the substitution here. We equal the let u equal to x minus 0.75. So integrate like they usually we do, and then we put the O at the end of the integration. So the last answer, we will get the mx in bracket T equal to 1 plus 0.88833t plus 0.48132 squared plus O in bracket 3 power of 3. So that's the final answer.
Overall, the experiments in this project provided a clear understanding of how probability and statistical methods are applied to the real-life data. Through collecting and analyzing multiple trials, we were able to calculate key measures such as mean, variance, and empirical probabilities. This result allowed us to compare actual observations with theoretical expectation and see how naturally variability occurs in human-related measurement. In addition, the project highlighted the importance of consistent data collection and the factors that may influence the accuracy of an experiment. By identifying possible outliers and source of error, we learn how to interpret data more critically and make more reliable conclusions. Through the experience, we strengthened our skills in statistical analysis and gained practical insight into how probability concepts are used to study real-world situations. Thank you.
like that.